This is a beaker of hot water and cold water. Which freezes first? Common sense says the cold water. But what if I told you the hot water could win the race to become ice? This bizarre phenomenon has puzzled scientists for centuries, and today we're going to find out. The idea that hot water freezes faster than cold feels wrong, but the observation dates back to thinkers like Aristotle. It was truly brought into the modern world in 1963 by a Tanzanian schoolboy named Erasto Mpemba. While making ice cream for a class, he was short on time and put his boiled milk mixture into the freezer while still hot. He soon discovered his hot mixture was frozen solid, while his classmates' cooled mixtures were still liquid. His teacher dismissed the observation, mockingly calling it Mpemba's physics. But Mpemba persisted, later asking a visiting physicist, Dr. Dennis Osborne. Intrigued, he confirmed the result, and they published a paper together, officially naming it the Mpemba effect. So why does this happen? Scientists don't have one single answer, but rather several competing theories. First is evaporation. Hot water evaporates faster, so it loses mass. Less water means less time is needed to freeze it. However, this mass loss is too small to fully explain the effect. Second, convection. In hot water, strong internal currents bring heat to the surface more quickly, increasing the overall cooling rate. Cold water has weaker currents, and a cool layer can form on top, acting like an insulator and slowing the process. Third, dissolved gases. Boiling forces dissolved gases out of water. Some scientists believe these impurities in cold water can interfere with the formation of ice crystals, giving the pure, previously hot water an edge. Finally, and perhaps most importantly, is supercooling. Water can often dip below its freezing point without turning to ice, a state called supercooling. Cold water is more prone to this. Boiling may alter impurities that prevent ice crystals from forming, allowing the hot water to start freezing sooner. We put it to the test. We took two identical beakers with the same amount of water, heated one to near boiling, and left the other at room temperature. They went side by side into the same freezer with a camera tracking the race. After about 2 hours, the result was remarkable. The beaker that started cold was still mostly liquid, but the beaker that started hot, it was almost completely frozen solid. The Mpemba effect happened right before our eyes. So, our experiment worked. But here's the catch. The Mpemba effect is real, but incredibly fickle. It only happens under very specific conditions. The container shape, freezer type, water purity, and starting temperatures all play a massive role. This is why it's so hard to replicate consistently, and why the scientific debate continues. The Mpemba effect is more than a party trick. It's a window into the complex behavior of water. It's a reminder that science is a fascinating, ongoing investigation with deep puzzles hidden in everyday life. So which theory do you think is the main culprit? Evaporation, convection, dissolved gases, or supercooling? Let us know your theory in the comments below.